This is our second video devoted to the topic of solutions. On this slide, which is the next one in the PowerPoint from the previous video, you will see that I have filled out everything about factors that affect solubility. There are three major factors that do this: the nature of the solute and solvent, pressure, and temperature. Different states of matter are affected in different ways for these topics. Solids and liquids as well as gases. For the nature of solute and solvent, like dissolves like. What this means is that things that are polar dissolve into things that are polar, and things that are non-polar dissolve into things that are non-polar. Water is a little unique because it can technically dissolve both, but if we have an example, such as oil and water, oil is non-polar and water is polar. That's review from a previous chapter, and they do not go together, so they do not mix, they do not dissolve. That's because they're different. However, something like salt and water, salt is ionic, which means it's the most polar it could possibly be, and water is polar, they dissolve. And if we put oil into something like hexane, which is a nonpolar substance, it would dissolve. For pressure, solids and liquids are not affected by pressure changes because they are not compressible. Gases, on the other hand, are. When the pressure increases, solubility also increases. That's because the gases are getting pushed into solution. Pressure is being applied, and the gases have no choice. They can't escape. Therefore, they go into solution. For temperature, the factor of solubility is different for each type. So for liquids and solids, as temperature goes up, solubility goes up. This is because temperature increases, kinetic energy increases, molecules move more, but our solids and our liquids move into solution. For gases, it's the opposite for the same reasoning. So as temperature goes up, solubility goes down. Temperature increases, kinetic energy increases. The gas molecules want to move more, but they want to move out of solution. They want to escape or expand. These will be important on your upcoming test. Now we're going to kind of switch gears, and instead we're going to talk calculations. We haven't done that just yet. Some basic information about calculations before we get into them. Concentration is defined as the amount of solute dissolved into a set amount of solvent or solution. Units for concentration depend on what we're actually calculating. So maybe it's grams per 100 milliliters. Maybe it's molarity, which we'll talk about. Maybe it's molality. Maybe it's a certain type of percent. And we'll cover all of these in the next few slides. Something that is concentrated versus something that is dilute is explained in the bottom picture there. Something concentrated has a lot of solute, but less solvent. And something that is diluted has a lot of solvent, but very little solute. The first type of calculation that we are going to do for solutions is a mass volume percent. It is expressed in the the grams of a solute in volume of solution. So it's grams per milliliter, and it's a percent, so we're going to multiply this by 100. So your equation is this: percent mass volume equals our grams of solute divided by our milliliters, that's important, the unit there, of solution, and then we multiply that by 100. So for the first example, it says a solution is mixed with 18 grams of NaCl and 0.3 liters of water. Find the mass volume percent. So we have our grams of solute right here, that's the 18, but we were provided with liters of water, so we need to convert that. There are 1,000 milliliters in a liter, so we end up moving our decimal 3 spaces to the right, and it becomes 300 milliliters. And then we would just have to divide. So we take our 18 grams divided by 300 milliliters, and we multiply by 100. There are a lot of equations within this unit, but mathematically they're not too bad. And we should get 6%, and we want 3 sig figs, so we would put 6.00%. In the second example, it's a backwards problem. There's actually multiple different ways that you can solve this. You're being provided with the percent and asked to calculate the grams. So you can plug everything that you know back into the equation and solve for the missing piece. That will work. Okay. You could set it up in proportions if you'd like as well. Or you can just do this, which I find is the easiest option. We're going to just convert our percent to a decimal, so that becomes 0.24. And then after we convert our percent to a decimal, we just take that percent times the given volume, and we get 60 grams. We need to put the decimal at the end for proper sig figs. This problem is basically a fancy way of saying, what's 24% of 250? And that's exactly what we did. Okay. On the next slide is another type of calculation. It's a mass percent calculation. This is expressed in grams of solute or given grams of solution. Okay. The equation here is very similar. So it's grams of solute divided by total grams of solution. So we're going to have to add some things together here, usually, times 100. And then the unit, of course, is going to be percent because it's a percent mass. Okay. So the example provided here says a solution is created with 0.14 moles of gold and 2.3 moles of platinum. What is the mass percent of the solute? Okay. So at this time we don't have the right units, so we do have to do some molar conversions. We're going to take our given moles of gold, and we are going to multiply it by its molar mass because we need grams. So the molar mass of gold is right around 197 over 1 mole, and we solve, and we get 27.58 grams. You do the same thing for platinum, and platinum has a mass of 195, so our 2.3 moles of platinum is 448.5 grams. And then we would just plug these gram amounts into our equation. It's really, really, really important that you remember that the total grams of solution, the sum, goes on the bottom. So I'm going to take my 27.58 grams divided by the sum of both of them, because it's the total. And then I'm going to multiply that by 100 because it's a percent. And you should end up getting right around 5.8%. Biggest mistake I see is forgetting to use the total, because with percents usually it's a part over a whole. So people like to do the smaller number over the larger number, but it's got to be the smaller number divided by the total mass. In addition, we can work backwards with these as well. So how many grams of KCl are needed to make a 250 gram solution if it's 28%? Okay. So here it's done the exact same way as before. I think it's easiest to just convert my percent to a decimal. So 28 becomes 0.28. And then I like to just multiply it by the given total. Okay, so 28% of 250 ends up being 70 grams. You have to put the decimal in there for 2 sig figs. In addition to mass percent, you could also potentially be asked to calculate PPT or ppm, which is parts per thousand and parts per million. Okay, it's the exact same fraction for both of them, so it's still grams of solute divided by total grams of solution. Okay, so that's the fraction. If it's PPT, we instead multiply by 10 to the third. If it's ppm, we instead multiply by 10 to the sixth. So you're just multiplying by a different factor. Okay. Now at this time, with that being said, it would be beneficial for you to pause the video and try the provided practice problems, and then we'll go over them. Please check your answers. For the first one, you had to first convert moles to grams by multiplying by the molar mass, and then convert your liters to milliliters because of the required units, and then you divided and multiplied by 100. For the second one, you needed grams of both, so again, multiply by molar mass, and then it's the HCl mass divided by the total times 100 to get 43%. For the percent mass oxygen, it was again 20 divided by the total times 100. And then for number 4, you use the same fraction, the 20 over 100, but instead you multiplied by 10 to the third, or 1,000. And then for ppm, same fraction times 10 to the sixth. Okay, let's continue our study. The next type of solution calculation is molarity. Molarity is the number of moles of solute per liter of solution. There are really multiple ways to do this, so the equation in and of itself is molarity, capital M, equals moles per liter. You can turn this into a triangle, like we have in the past, and then potentially cover up what you're looking for and solve. You can either solve this in steps or all as one through dimensional analysis. So, first step would be to convert your grams to moles. We do that by dividing by molar mass. Second step is to convert your milliliters to liters. We do that by dividing by 1,000. And our third step would be to divide both answers. So, your answer to number 1 over your answer to number 2. That's one way to solve. The other option you have is to just do dimensional analysis, and this is the method that I prefer personally. So what you would do instead is you would take the given grams over your given milliliters, and then you would do 1 mole of the given over its molar mass. And then you would do 1,000 milliliters in 1 liter. Both ways will work. Finally, you could be asked to solve a backwards problem, so you could be asked for grams instead. And here what you would do is you would have your liters times your molarity to get moles. And then you take your moles times your molar mass to get grams. We will continue the examples and the rest of this PowerPoint in our next video.